Now, my talk is, it's not really econometrics. It might fall into somewhere like happiness economics, I'm not sure. I should also say that divorce is one of those topics that people either treat as a joke or get extremely angry, and I don't mean to upset anybody. So whatever your particular emotions are, bottle them up if you don't mind. I'm doing this with Andrew Grant, who's a colleague at Sydney University, and there's a third author in effect called Bernd Scherer, who inspired the paper by writing a very angry divorce paper. This is a very mellow divorce paper. So the financial issue, I guess, is that I read a bit of the slide, but I should also say there's about 42 slides in a 30 minutes, so we're going to go rather quickly. Does the risk of getting divorced affect the portfolio decisions of investors? And there are clear issues about divorce and how it might affect your wealth, which are well documented in every tabloid. I'm sure you all know that. We're going to put all this in a framework in a two-period model with consumption and investment. It's a classic finance model. It's discrete time. Our agent in the model is a couple who make joint decisions. We're not interested in division within the couple. So if there's a transfer of £1 million from the wife to the husband, that's neutral. It's total couple welfare. We're also very eclectic. We do not care what a couple is. It could involve N entities as long as there's more than one of them. You might think of it as a partnership or a business. And then we're talking about dissolution. The twist on this is that our utility function doesn't just depend upon wealth, but on something which we'll call marital happiness or whatever. And that makes it really very different from the finance literature, because when you look at the finance literature, all of finance is based on the idea that you maximize the expected utility of wealth. And even in cases when there are other variables in the problem, such as health or whatever, health is a bad example. Health is one of the few examples where there is research where it comes into the utility function, but examples like, for instance, weather, or other sorts of background risks are all converted back into wealth and monetized, if you like. So again, you're returning to a univariate utility function. We're going to move it into a different framework. We're also going to make divorce endogenous. In many papers, not every single one, but most of the divorce literature, divorce is an act of God. You know, God tosses a coin, you get divorced or you don't. And this, well, that sort of, I think, has a Greek origin as much as anything, but in any case, we're going to make it endogenous. So it's going to be as a consequence of marital quality. And so our current consumption investment decisions are going to be affected by this. The probability of divorce will be influenced by the success of couples' investments, and of course that's a function of cost. We've said the couple derive utility from marital quality, but the key point here is they don't know that at time equals 0. So in this artificial world, by the way, this has nothing to do with reality, so I don't need to be told that this isn't real, because it's not, it's a model, just so that we've clarified that. All our couples start being married at time equals 0. They observe their marital quality at time equals 1. And at time equals 1, they decide to get divorced or not, depending on the outcome. So, as I say, the key calibrations are the cost of divorce and the time to revelation of marital quality. So that's the basic structure. Today, consume and invest. Tomorrow, observe investment returns of marriage quality, divorce or not. Very simple model, very simple structure. But you can see here that this is endogenous. Okay, literature there's lots of papers written on this, but none of them really do what we're doing. Empirical studies, again, I guess the best bit is that someone who works on divorce studies is called Love. Bad, isn't it? I mean, there's a very extensive literature on family economics, some of which is extremely interesting and clever. Just one thought-provoking idea. Marriage provides a method of risk sharing. I think you chaps and chapettes need an algebra fix, so let's get into it. So here's my current utility of consumption. R is my portfolio returns. Think of W as a vector of weights and R as a vector of returns. Riskless rate is R1. my expected utility is my current utility of consumption discounted by the discount rate, expected utility of what I invest times the return I get on my investment, minus a fixed cost of divorce D times I1, which is a variable I choose in the future, which is going to be 1 or 0 depending if I get divorced or not. If I get divorced, I subtract the cost. If I don't get divorced, I experience marital bliss, where psi theta is the utility function, or psi theta is the utility function of marriage, and theta is the actual value of marital quality. That's the basic structure. I'll take questions if anyone wants points of clarification. If everyone's happy, I'll continue. Okay, so there's a list of the variables. As I say, the couple pays divorce cost D if they get divorced and do not receive the marital quality realisation psi theta. So what happens here is if you get divorced, you don't get that. Okay, initially we assume they're risk neutral, so I just set psi equal to theta. And if you do that, you can actually sort of write out the problem to the extent that you can get an explicit formula for the probability of divorce just by rearranging this, and that's what we do. And that has an attractive interpretation because you can effectively rewrite this slightly complicated optimization problem in terms of this probability P, but the point to note is that the probability P depends upon the random variables as well. So it's effectively, it is a probability, but it's a random variable in its own right because it's going to depend upon what the returns actually are. So we get this framework here, and this is just a rewrite of the original problem. And that's really just setting the scene for what we're going to do, because this model has a lot of limitations to it. I think we can just move forward, and we're going to look at it in a slightly more general way. And it turns out there's a very general literature out there, particularly in the operations research, on what's called multi-attributed utility functions. And they're immensely interesting. And so what we did after skirmishing around with what economists might do, we actually started looking at that. And that's really what I'm going to talk about today. So far I've just given you an intro to the problem, but what we're going to do now is focus on what are called mixed-X utility. And how this works is we put it in a framework where you essentially have a risk aversion to wealth, as you always do in a conventional utility problem, but you also have a risk aversion to marital quality. And there's in effect 4 variables in the problem. There's wealth, marital quality, and 2 risk aversions. And we're going to treat those risk aversions in this framework as being essentially stochastic. And the reason we want to do that, we want to set this up in a particular way because we want to get the interaction between these two, and you have to be careful to do this because in a very simple framework where you have, say, multiplicative utility, so utility, the joint utility is the product of, if you like, the individual utilities, and if you also assume W and theta are independent, what you get as a result, which essentially says that the gist of this result is that the actual, well, hold on, there's a lot more to there's more details to the result, but let me just go to the punchline. We'll get to the punchline eventually. The punchline is that we're basically delinking any connection between asset selection of our wealth and the characteristics of theta. So what that result is establishing is that under certain conditions, basically investment's independent of your personal life, and that's not the result we're interested in, so we're going to move it to a slightly different framework. And this is where we get into the particulars of mixed-X. The work on this has been done by numerous people, but the key recent papers are Satchell and Winkler, which may be in management science, and let me just quote the result. It proves that in a multi-attribute context, if our preferences involve preferring the lottery combination of good and bad versus the alternative of good with good and bad with bad, then our multi-attributes utility functions must be of the mixed-X form. Well, I haven't defined mixed-X yet, but it'll be on the next slide. But let me just explain what that is saying. What that is saying is that I could have a world over 2 things. So you could have, for instance, a spectacular marriage and an immense amount of wealth versus a terrible marriage and very small wealth. That's a choice between 2 alternatives. The other would be a fantastic marriage and low wealth versus fantastic wealth and bad marriage. And Mixed-sex utility folk prefer the latter choice to the former choice. So you rather mix across good and bad than good with good versus bad with bad. Now, intuitively, that's what most people would do. The consequences of doing that is you get a particular form for your multi-attribute utility function. And it's quite a remarkable result. I've just given an example here in terms of wealth levels and marital quality. So the good combination would be high wealth and high marital quality. A bad is low wealth, low marital quality. And then these are low wealth, high marital quality, high wealth, low marital quality. If we prefer a 50-50 choice with these versus a 50-50 choice with these, then we're going to have mixed-sex utility. It also has a name called correlation aversion, because clearly these things are strongly positively correlated. So here's mixed-sex utility. It's very beautiful. Now, for those of you who like moment generating functions and cumulant generating functions, welcome, because notice the format. The utility of wealth and marital happiness is essentially a joint moment generating function taking over the distribution of your stochastic risk aversion for wealth and your stochastic risk aversion for marital happiness. And therefore, whatever we know about moment generating functions, which hopefully is quite a lot, will apply to this problem. U scaled here. As I said, x and y can be loosely interpreted as stochastic coefficients of risk aversion and a bivariate exponential utility. PDF xy is just the PDF of the risk aversions. It can be discrete, and in the examples we look at, it is discrete. Okay, so that's the actual, that preference of choosing good bad alternatives essentially gives you that utility function. I have to say it's not an obvious result. So what does risk aversion to marital... We all know what risk aversion to wealth means, but what does risk aversion to marital quality mean? Well, it's a little tricky. So here's a few pointers on it to give you some insights. It might be seen as something that's genetically inherited, but there is some evidence that actually that genetic divorce occurrences don't seem to, they're not a strong correlation between what happens in a parental marriage and children's marriage. There is some, but it's not the most important. There is a sort of a concept in the demography literature called propensity divorce, but they don't define it, but it's in a sense similar to this concept. So as you do in the social sciences, you replace one idea you don't understand with another idea you don't understand, and you feel you've made some progress. A third example is perhaps heightened sensitivity marital quality risk, which might be observed in terms of, wedding expenses, anniversaries, partners' birthdays, etc., etc. It's interesting to note that there may be a sort of some kind of ethnic or racial element to it, because the divorce rates between different ethnic groups in the US, that's 5 years in, first marriages, are quite, so for instance, I think it's 10% on average, but Asian are 3% and Hispanic are 7%. So there's clearly some sort of cultural explanation for this. And there's also quite a lot of evidence on the role of religion. So for example, intra-faith marriages have a much lower divorce rate than interfaith marriages. So if you marry across religions, the divorce rate tends to go up. So all of these things may be linked in some sense to this concept without precisely nailing it down. So we're going to now assume that this is bad. There's a number of notational glitches here, but all good talks should have a notational glitch because it keeps the audience awake. So here we're going to assume that mixed-sex utility. We're going to have pseudo probabilities. These are P1 and P2. If it's P1, you get alpha 1 and beta 1. If it's P2, these add up to 1. You get alpha 2 and beta 2. So they're the risk aversion. You could think of this as perhaps high or low or whatever the numbers are, risk aversions. And as we come down, that describes an actual distribution. It's pretty parsimonious. In fact, it's possibly too parsimonious, because you can sort of see here that if you have only 2 points for a pair, there's going to be a perfect correlation between them. It's not obvious. If you write out the distribution of this thing, these two variables are going to be correlated. So here we are, we write out what our model's going to look like. We've dropped divorce temporarily, that's just the utility with respect to these two things. Notice now that my risk aversion is changing as I move. You can think of these as different states of the world. This is where I've got high risk aversion, maybe this is where I've got low, this is where I've got high or low marital risk aversion, high or low marital risk aversion. And then when I look at the divorce case, it's much the same. I'm going to look at what happens if I do divorce versus what happens if I don't divorce. So this is a not divorce, this is a divorce case. And now we can solve this numerically, but it's much harder to solve it in terms of an explicit probability. We can't do that, so we do it numerically. Now, another way of thinking about this equation, though, 39 was here, but I took it off, I'm sorry. The expected utility can also be thought of as a moment generating function evaluated across 2 points. So it's a moment generating function of, let's get it the right way round, of the two random variables r and theta. And you can put it in terms of those arguments. Okay. That was good, thank you. That allowed me to catch up with where I was. Well, I'm not sure we'll learn too much from that slide, but let me see, where will we pick up the story again? So essentially we've got the structure here, and this is the basics. You can imagine a structure here where I've got my two variables. Here are the values they take, here are the two values here, and rather than just have this rather constrained space where they're perfectly correlated, we now allow all four combinations. And that means that instead of having a structure where we have just two terms in our, let me go back, the only difference here is here we've got two terms, now we're going to have four terms, but otherwise it's essentially the same problem. Okay, so let me just go forward and let me get to the first interesting result. Now, in finance, so we're going to do some finance now, believe it or not. I really just started talking about divorce to lead into the fact that actually there are interesting multi-attribute financial problems. And for divorce, it really could be, or marital happiness could be happiness, could be value, could be the quality of the asset. It could be a whole bunch of other attributes for which you get direct utility rather than indirect utility via wealth. So looking at the broad framework, we're now going to come back and look at this utility, and we're going to define certainty equivalence. And this, I believe, is probably new, at least we couldn't find it anywhere in the literature. And for those of you who, I assume you all know this, you know the classic result when we do this, let me go ahead. Certainty equivalence conventionally is this. So what you assume is you've got normal returns, an exponential utility, you take a transformation, and this is the certain return. And why you do that is it's a justification for doing mean variance analysis. So when I do certainty equivalence, I can get to a point where I can do actual mean variance analysis and work directly with this. But its interpretation is it's the certain amount of wealth that I get that will give me the equivalent utility to my expected utility problem. Now we're going to try and do the same thing here. So I'm going to define certainty equivalence in the same way that it's a certain amount of wealth. It doesn't depend on the random A's anymore. It just depends on a certain amount of wealth, but it will depend upon the risk aversion. Now, when one thinks about that, certainty equivalence must depend upon risk aversion. And if your risk aversion changes, your certainty equivalence should change. So we postulate that our definition of certainty equivalence is going to be called C lambda. And then modulo, I think, a minus sign in the wrong place. We can see that this thing here, so this is the expected utility, but if I go back to the original here, I can also think of this as being the expected utility, or the expected utility is equal to this integral, which is the moment generating function of the attributes A taken over the risk aversions lambda. And we're going to make the, I think, fairly innocuous assumption that the attributes and the lambdas are independent. We don't need to do that because we can just write it all in terms of conditionals as well, but it's just easier to, so we can write everything like this, but we're not going to do so. And the fact is that I can write e to the log without changing anything, so I do. And we all know that the log of this isn't a minus sign there, sorry, that is a typo. I can write this in terms of the cumulant generating function, which I do. As you know, log of a moment generating function is a cumulant generating function. And then it's a messy thing now because it's n-dimensional. So I'm going to switch into tensor notation. So i's just mean I'm summing over I, and ij means I'm summing over I and j. And so the first term here is like a cross product. This is like a quadratic form. And now we get a, I don't know what you call this, a cubic form and a quartic form and so forth. But what we have here are basically functions in terms of the cumulants of my attributes and the various risk aversions. So because I can write it like this, I now have a formula for the certainty equivalence, and it's in this context of this utility function, the certainty equivalence is a function of the cumulants and the lambdas in a rather splendid way, and that is it there. So we notice that the first one are the means, the second one are the covariance matrix, and we end up with this result, as I say, that the certainty equivalence can be written in this general form. And that's awfully nice, but then the trouble comes, well, you need some joint distributions to understand what this is going to be like. And the only joint distribution that's easy to work with, alas, is the multivariate normal. So it's no surprise that we get to this corollary that if we assume that the A is a multivariate normal and that A and lambda are independent, then the certainty equivalence is going to be mu, which is a vector, because the means of all the different attributes, minus a half sigma, which is a covariance of all the different attributes, times the lambdas, which is a vector of attributes. And so we get that as a general result, and if I now have only one attribute, i.e. wealth, I get back to the special case of certainty equivalence that's very familiar. I love it. You may hate it, but I love it. Okay, so now in broad terms, this is simply saying that we have a risk-adjusted attribute vector where the scale of the risk adjustment, lambda, is variable depending on the state of the world. So it's exactly what it should be. So if I told you that if something happened, your risk aversion was 2, but if something else happened, it was 3, you would postulate that that's the correct formula, and that's what we get out of this. Okay, so now we're going to move it on and think about optimizing. How am I going for time? I've got the blood up. There's one good result and we can scrap the rest of the talk. So I'm now going to regard my first attribute, as being a portfolio of returns. So we know what mu1 is. I'm assuming that they're normal. And I'm going to define sigma 1,1 is clearly going to be the variance of the portfolio. Sigma 1,2 is interesting. It's the covariance of the stocks or assets with the attributes. So it's the relationship between, I don't know, IBM and marital quality and, various other companies. And so we have a matrix here which we need to specify. I'm going to split these up into their subpartitions. I'm going to do some optimization and solving. And I end up with, a messy expression, but let me just go straight to the first order condition. The first order condition looks like this. This is not a solution though, because in here, the G functions also depend upon the weights. So the way we interpreted this rather murky equation is it's sort of like a dynamic updating relationship. If I knew the weights at time n minus 1, I could then work out the weights at time n. And if we do that, I need a few definitions here. So I'm defining these various functional forms at different times based on different weights. I end up with this relationship. I get the weight at time n is equal to this portfolio times some weight function minus this portfolio times some other weight function. Now, as these 5 minutes, I'm there. As these weights change, these numbers change, but these portfolios stay the same. So if we look at those portfolios, what actually are they? Well, the first portfolio is essentially the Markowitz portfolio. It's the standard market portfolio out of mean variance theory. This one is your classic hedging portfolio. You could regard it in some sense as being, it's like a beta. It's the beta of the stocks on all the assets. And there are any number of formulae that say that. That is to say that you're going to, any of your standard ICAPMs and so on have typically a market portfolio and hedging portfolios. So you might say, well, you haven't done anything different. The first one on the right is the Markowitz. The second is a vector portfolio adjustment for hedging correlations. These are scaling factors. I call these factor mimicking portfolios. But let me go back and just clarify this point. This is n. This p is actually a set of weights, so there's n minus one of them. So these just contribute to the size of your hedge, if you like. The difference in what I'm doing here from what other people have done in the past, what we're doing here, I'm sorry, is that we're looking at a situation where we have multi-attribute utility. So this is actually telling us how our investment hedges our happiness, if you like, or whatever these other things are. And that's exactly what the results show. 2 minutes. Some of the calibration so wonderful, I'm going to overshoot by 1 minute. So now we're going to wait. Now, how long before marital quality is revealed? It's a key question, isn't it? How long would that take? Well, Marilyn Monroe's famous film, The 7-Year Itch, well, it's not called The 7, it was called The 7-Year Itch, suggests 7 years. So we think, is there any evidence for this? Let's have a look. Let's probably not, we'll leave that one for the moment. So here's some evidence from Australian Bureau of Statistics. In Australia, before you get divorced, you get separated. You get separated pretty constantly at about 8.5 years. But you don't get separated spontaneously, so the marital, it takes perhaps, who knows, 18 months. So the evidence, and there's a lot of other evidence, that 7 years is the waiting time before marital revelation occurs, marital quality revelation. 7 years seems about right. We want to do divorce costs, we put them at about 20%. There's a lot of evidence that that's about right from your wealth of the couple going into the divorce. This is just evidence on that. This is interesting. Just one thing on this. This says the divorce rates of all the different countries. I've only given this talk once before, and it was at a Russian hedge fund. Now let's look. Let me see. Yes. You can see here that was some raised delicate social issues. I'm sure that I hope all your countries are at the lower end of it all. Essentially why the divorce rate is higher in Russia is to, this is per annum by the way, it's to do with the fact that divorce costs are very low there. You know, you can just sort of unwind the relationship. And although that's also true in some Muslim countries, for example, there are other cultural constraints, which doesn't say Iran keeps it low. Anyway, enough of that. We make usual assumptions about returns. We make an assumption that marital bliss is normal with a mean of 0.1 and a variance of 1/12. Let's move on. We then look at, we think that the interesting action here is happening between the correlation between returns and marital bliss. So we take a range of values between minus 0.9 and plus 0.5. And what would that tell us? Well, if we just go back here, let's just get the intuition of this, and then I'll probably stop. Sorry, here we are. This thing is, think of this as a correlation. If the correlation's negative, loosely speaking, because these things should be positive, they are under weak conditions, that would increase our equity position. So what that's saying is that intuitively, what is that saying? That's saying that if I know that my low wealth state is likely to be compensated by a good marital state, I'll invest more in equity. And that's exactly the result that the model shows. And I'll just finish on that note. We go to the end here, we get a table of results, and that's exactly what comes out of the results. Demystifying, B is the proportion we're holding in equity. You can see here it's going up as the correlation becomes more negative, which is what the model predicts it would do. And here we've got the expected probability. We calibrate this to get numbers that look about right. We'd expect this to be around about 10 to 15% after 7 years. So that means that seems to happen at costs of 20%. We also compute our initial consumption, which is actually a bit irrelevant to the story, but we kept it in there. And also we've got expected probability. The key things we're looking at actually are expected probability and the percentage in equity. And you get this clear relationship. Now that's an intuitive story, and we've done a lot of work to establish it. We look at various combinations of P11, P12, depending on whether alpha and beta are co-correlated or negatively correlated, and we look at different results. And I think we can stop there and I'll take questions.
Thanks, Ted.